when the stress induced in the material, when the stress induced in the material exceeds the endurance limit of the material, in that case what will happen, the component will take up, or the component will function for a particular number of cycles, and then it will break, right? Now if the stress induced in the component is well within the endurance limit, the component will not fail, right? That is what the concept of endurance limit means. Now then what happened, as we know, the component will usually be subjected to a combination of bending and twisting moment when we used to determine the endurance limit of the material. Now what will happen if the component is subjected to different types of loading simultaneously? Then what happened, in a similar fashion like theories of failure, certain models were proposed by different scientists which predicted the failure of a component when it is subjected to fatigue loading. Now, three most popular fatigue strength models will be discussed now. So the first one is called as Soderbergh's model. The first one is called as Soderbergh's model. Now, what we do, as you can see, I have a graph wherein I have mean stress along x-axis. The mean stress is considered along x-axis, and the stress amplitude is considered along y-axis. The variable stress is nothing but stress amplitude. I have stress amplitude along y-axis. Now basically what I am trying to do, I am trying to plot a graph of stress amplitude which was called as sigma A, the stress amplitude versus mean stress. If I take a plot of this, now what will happen, for a given scenario within the material, the component can be subjected to different combinations of stress amplitude as well as mean stress. Now what this guy Soderbergh did, he took a material, then he took this component of mean stress along x-axis and variable stress or stress amplitude along y-axis. He marked a point corresponding to the yield strength of the material. He marked a point corresponding to yield strength of the material, that is sigma y on x-axis. Then he considered another point, that is endurance limit of the material. Endurance limit of the material, in our case, we will be representing it as sigma minus 1. He took a point corresponding to the endurance limit of the material along y-axis. He marked these 2 points. Then he joined these 2 points using a straight line. Then what he predicted, if a component is subjected to any stress which is well within this triangle, if the component is subjected to any stress value which is well within this triangle, the component is safe. That is, say, let me assume that the endurance limit for a particular material is 120 MPa, right? And correspondingly, the yield stress may be somewhere around 150 MPa. Let me assume it this way. Okay. In order to illustrate it, I am considering certain values. Now, what will happen if the mean stress induced in the component? What is mean stress? Mean stress is the average of the maximum and minimum stresses. Now, if you can recall from the previous class, mean stress sigma m is nothing but sigma max plus sigma minimum divided by 2. If the mean stress induced in the component is less than the yield strength of the material, then also if this stress amplitude, that is sigma a, if the stress amplitude, what is stress amplitude? Stress amplitude is half of the difference between maximum and minimum stresses. This is stress amplitude. If the stress amplitude is less than the endurance limit of the material, if both these conditions are met, then the design is safe. or else the component will fail. This is what Soderbergh predicted. So this is also one of the most important questions that will be asked in your examination, ideally for 5 marks. So what will be asked? They will ask you to state Soderbergh criteria, and they will ask you to derive an expression for it. Now basically understand what we do. We consider a typical y-axis graph. In y-axis we have stress amplitude, that is sigma A. In x-axis we have mean stress, that is sigma M. And also remember, if the from moving towards right of the x-axis, this it means that the stress is tensile, and if we are moving towards the left of the x-axis, then the stress is compressive. This is one thing to remember. Now what this guy Soderbergh did, he considered a point corresponding to the yield strength of the material on x-axis. He marked that point, and also he considered the endurance limit of the component along y-axis. ಎರಡು ಪಾಯಿಂಟ್ ಕನ್ಸಿಡರ್ ಮಾಡ್ಕೋತಾರೆ. So then he will join those 2 points using a straight line. Then what is his prediction? If the component is subjected to any value of stress well within this triangle, it means that the design is safe. This triangle ಒಳಗಡೆ ಎಲ್ಲೇ ಇದ್ರೂ it means that the design is safe. If not, here in this case the design is safe. This triangle ಒಳಗಡೆ ಇದ್ರೆ, if you go anywhere outside this triangle, the component will fail. This is what Soderbergh said. ಅರ್ಥ ಆಗಿದೆಯಾ ಇದು ಕಾನ್ಸೆಪ್ಟ್? Is the concept clear? Suhas? ಅರ್ಥ ಆಗಿದೆಯಾ ಕಾನ್ಸೆಪ್ಟ್? ಓಕೆ, ಇನ್ನೊಂದ್ಸಲ ಹೇಳ್ಬೇಕಾ? ಅರ್ಥ ಆಗಿದೆಯಾ? ಬೇರೆಯವರು? ಭುವನ್?
ಸರ್ ಅರ್ಥ ಆಗಿದೆ.
Okay, fine. Now this is what is called as Soderbergh model. This is what is called as Soderbergh model. The most important thing that you should remember is along x-axis, Soderbergh is considering yield strength of the material. Along x-axis, Soderbergh is considering yield strength of the material. Then there came another guy. Called Goodman. Then came another guy called Goodman. So what he did, he considered ultimate strength of the material. He considered ultimate strength of the material along x-axis. He considered ultimate strength of the material along x-axis, as is indicated here. Then he considered the same endurance limit along y-axis. Yield strength na consider ಮಾಡ್ಕೊಳ್ಳೋದ್ರ ಬದಲು he is considering ultimate strength. So you always know ultimate strength will always be greater than yield strength. So it is towards the right along x-axis. So then what will happen? He joined a line. He drew a line with joined endurance limit and ultimate strength. Yield strength ತಗೊಳ್ಳೋದ್ರ ಬದಲು ultimate strength ತಗೊಂಡಿದ್ದಾನೆ. So ಈ first line ಎಳೆಯೋದ್ರ ಬದಲು he has to do the second line. Now what does he mean? So if you consider any value of stress within this triangle, that is what will happen? What will happen in the case of Goodman? What will happen in the case of Goodman? If the mean stress is less than the ultimate strength of the material, if the mean stress is less than ultimate strength of the material, and if the stress amplitude is less than the endurance limit of the material, in this case the design will be safe. Andre no, e line, e triangle ಒಳಗಡೆ ಇದ್ರೆ the design will be safe. But if the stress value go beyond this triangle, the component will fail. That is what Goodman did. So the only difference between Soderbergh and Goodman being, Soderbergh considered the value of yield strength along x-axis. Goodman is considering the value of ultimate strength along x-axis. This is the only difference, barring which every other condition is same. Is artha idea concept? Is the concept clear? Prajwal MC? ಪ್ರಜ್ವಲಿಂಸಿ. ಋತ್ವಿಕ್,
ಎಸ್ ಸರ್.
ಅರ್ಥ ಆಗಿದೆಯಾ ಕಾನ್ಸೆಪ್ಟ್?
ಹ್ಞೂ ಸರ್, ಗೊತ್ತಾಯ್ತು.
Okay, fine. Now, lastly, there was another guy by the name Gerber. Just give me a moment. There was another guy by the name Gerber. Now, what he did, he then considered the Goodman line itself and then he modified it. So what this guy Gerber did, he considered the same endurance limit along y-axis, he considered the same ultimate strength along x-axis, but instead of joining a straight line, he drew a parabola. As is represented here. He drew a parabola like this. Then what he said, any stress value within this parabolic limit, if this is the case, the component will be safe. If you consider any stress value that is beyond this parabola, the design is not safe. Now, this is what he said. So basically, you try to understand this way. So we will begin with Soderberg. What Soderberg did, he considered sigma y along x-axis and sigma -1, that is endurance limit along y-axis. He drew a straight line that joins sigma y and sigma -1. He told that if the stress value, if the state of stress is well within the triangle, the design is safe. Goodman modified it. What is the modification that he did? Instead of considering sigma y, he considered sigma u, that is ultimate strength. Instead of yield strength, he considered ultimate strength, and he repeated the same thing. This is the second condition. Now, lately, what this guy Gerber did, instead of drawing a straight line, he considered the Goodman criteria itself. Instead of joining a straight line, he drew a parabola. So this is all the modification that they have done. Now, if you observe these things, these hypotheses are the concept that they are stating, or the model that they are presenting in front of us, is based on experimental data. Now, what they did, they took a component, they put it onto a fatigue testing machine. Then what they did, they subjected the component into different stress levels. So the component might have a stress level of, say, a mean stress of 100 MPa, stress amplitude of 70 MPa. They took it, they subjected it to testing, and they conducted the experiment for somewhere around 10 to the power of 6 cycles, and the component did not fail. For any stress value, if the component failed, they marked those points as is indicated by these zeros here. ಈ ಝೀರೋಗಳೆಲ್ಲ ತೋರಿಸ್ತಾ ಇದೆಯಲ್ಲ, ಈ ಝೀರೋ ಎಲ್ಲ ಫೇಲ್ಯೂರ್ ಪಾಯಿಂಟ್ಸ್. ಅವ್ರು ಏನ್ ಮಾಡಿದ್ರು, ಫೇಲ್ಯೂರ್ ಪಾಯಿಂಟ್ ಎಲ್ಲಿದೆ ಅದರಿಂದ ಕೆಳಗಡೆ ಒಂದು ಲೈನ್ ಹೇಳಿದ್ರು. ಈ ಲೈನ್ ಒಳಗಡೆ ಇದ್ರೆ ಸ್ಟ್ರೆಸ್ ಲೆವೆಲ್ ದಿ ಕಾಂಪೋನೆಂಟ್ ಇಸ್ ಸೇಫ್ ಅಂತ ಸ್ಟೇಟ್ ಮಾಡಿದ್ರು. This is how the models were established. Now, when we try to refer, or when we try to correlate this with respect to experimental data, the Soderberg's criterion is best suited for ductile materials. So whenever we are designing components made of ductile materials, we will always make use of Soderberg criterion. ಅಂದ್ರೆ ಏನು, ಬೇಸಿಕಲಿ ಸಿಮಿಲರ್ಲಿ ಮ್ಯಾಕ್ಸಿಮಮ್ ಶಿಯರ್ ಸ್ಟ್ರೆಸ್ ಥಿಯರಿನ ಡಕ್ಟೈಲ್ ಮೆಟೀರಿಯಲ್ಸ್ ಹೇಗೆ ಅಪ್ಲೈ ಮಾಡ್ತಾ ಇದ್ವಿ, ಅದೇ ತರ whenever we are encountering ductile materials under fatigue loading, we will always make use of Soderberg criterion. For brittle materials, we will make use of Goodman criterion. And basically, we are interested in deriving an equation which represents this line for Soderberg criterion and an equation which represents this line for Goodman criterion. Since this is a parabola, the equation that we are going to get will be non-linear, owing to which we will not make use of Gerber's criterion much. For most of the cases, this is not such a great approximation of the strength of the material. So even in your syllabus, we are restricted to Soderberg criterion as well as Goodman criterion. Now let us try to derive an expression for Soderberg criterion. So ಇಲ್ಲಿ ನಿಮ್ಮ ಹತ್ರ ಇದಿದ್ರೆ, you just take a sheet of paper and a pen and let us try to derive an expression for Soderberg criterion. Now what we will do, Give me a moment. Now, what we will do, we will try to plot a graph. Another doubt idre, you can stop me at the anywhere and you can get the doubt clarified. This is very important derivation. We are deriving an expression for Soderberg criterion. Idana barkoli, you mark it as important. Now what we will do, we will try to draw a graph. Let us consider mean stress along x-axis. We are considering mean stress along x-axis. What is mean stress? Sigma m. We are considering sigma m along x-axis. This is sigma m. And then let us consider stress amplitude. That is sigma a along y-axis. Along x-axis, we have mean stress sigma m. Along y-axis, we have stress amplitude sigma a. Then what I will do, on y-axis, I will mark a point. On y-axis, I will mark a point that will correspond to endurance limit of the material. I will mark a point that corresponds to endurance limit of a material, and by our convention, the standard notation that we follow for endurance limit is sigma minus 1. So sigma minus 1 is endurance limit of the material. So what I am doing, I am considering a point on y-axis that corresponds to endurance limit of the material that I am considering, and I am calling that point as A. ಅರ್ಥ ಆಗಿದೆಯಾ? ಸೊ ನಾನು ಏನ್ ಮಾಡಿದ್ದೀನಿ, y-axis ಅಲ್ಲಿ ಎಂಡ್ಯೂರೆನ್ಸ್ ಲಿಮಿಟ್ ಎಲ್ಲಿ ಬರುತ್ತೆ ಆ ಪಾಯಿಂಟ್ ನ ಮಾರ್ಕ್ ಮಾಡ್ಕೊತಾ ಇದ್ದೀನಿ. ಆ ಪಾಯಿಂಟ್ ನ ಎ ಅಂತ ಕರಿತಾ ಇದ್ದೀನಿ. Then what I will do, I will mark another point along the x-axis which corresponds to yield strength of the component. ಸೊ ಇವಾಗ ನಾನು ಯಾವುದೋ ಒಂದು ವ್ಯಾಲ್ಯೂ ಆಫ್ ಸ್ಟೀಲ್ ತಗೊಂಡಿದ್ದೀನಿ ಅಂತ ಹೇಳಿದ್ರೆ, ಎಂಡ್ಯೂರೆನ್ಸ್ ಲಿಮಿಟ್ ಏನೋ ಒಂದು 100 MPa ಇದೆ ಅಂತ ಅನ್ಕೊಳ್ಳಿ. ಸೊ yield strength ಒಂದು 150 MPa ಇದೆ ಅಂತ ಅನ್ಕೊಳ್ಳಿ. ನಾ ಎರಡು ಪಾಯಿಂಟ್ ನ ಎಲ್ಲಿ ಸ್ಟ್ರೆಸ್ ಆಂಪ್ಲಿಟ್ಯೂಡ್ ಇದೆ ಅಂದ್ರೆ y-axis ಅಲ್ಲಿ ಐ ಆಮ್ ಮಾರ್ಕಿಂಗ್ ಸಿಗ್ಮಾ ಮೈನಸ್ 1, x-axis ಅಲ್ಲಿ ಐ ಆಮ್ ಮಾರ್ಕಿಂಗ್ sigma y, that is yield strength of the material. So what did Soderberg do? Soderberg considered these 2 points and he drew a straight line that joined sigma minus 1 and sigma y. I will do the same thing. I will draw a straight line which joins point A and B. That is, I will draw a straight line which will join the point that represents endurance limit on y-axis and the point that represents yield strength of the material along y-axis. Now I have drawn it. Now basically what we will do, being designers, I am stressing this point often, we try to be on the conservative side. We will always incorporate factor of safety. ಹೌದಾ? ಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಸೇಫ್ಟಿ ಹಾಕ್ಬೇಕು. ಈ ಮೆಟೀರಿಯಲ್ ಪ್ರಾಪರ್ಟೀಸ್ ನ ನಾವು ಏನ್ ಮಾತಾಡ್ತಾ ಇದೀವಿ, it might not be determined accurately and always there will be some unforeseen factors. There will be some unforeseen factors which will try to increase the magnitude of force that is acting on the component, or which will try to decrease the strength of the component. Now, in order to accommodate these factors, we will always make use of factor of safety. ನಾನು ಏನ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ, so in order to be safe, rather than considering this to be the safe line, what I will do, I will consider another point along y-axis. So ಇವಾಗ sigma minus 1 100 MPa ಇದೆ ಅಂತ ಅನ್ಕೊಳ್ಳಿ. If the endurance limit for the material that I am considering is 100 MPa, say I will take a factor of safety of 2. I will take a factor of safety of 2 and then I will divide this endurance limit by 2. So the modified endurance limit will be somewhere here. Endurance limit by factor of safety. I will consider another point which will represent the safe endurance limit. ಇದನ್ನ ಯಾಕೆ ಮಾಡ್ತಾ ಇದೀವಿ? We are doing this just to be on the safer side. So what I have done, I have considered a particular value of factor of safety which is represented by Fs. I am dividing the endurance limit by factor of safety. Say for example, if the endurance limit were to be 100 MPa, if the factor of safety that I am considering is 2, then the modified endurance limit would be 50 MPa, which is represented by this point. Right? So I am considering another point C, which will represent sigma minus 1 by factor of safety, which can be called as safe endurance limit. Right? Then what I will do, I will repeat the same thing for yield strength as well. ಹೌದಾ? ಸೊ yield strength ಗೂ ನಾವು allowable stress ಡಿಫೈನ್ ಮಾಡ್ಬೇಕಾದ್ರೆ ಏನ್ ಮಾಡ್ತಾ ಇದ್ವಿ? Allowable stress was defined as yield strength of the material by factor of safety. Similarly, in order to be safe, I am dividing this yield strength of the material by factor of safety. So suppose yield strength 200 MPa idre, now the modified yield strength or the safe or the allowable stress for this material will be 100 MPa. So I will do it. I will mark a point that represents sigma y by factor of safety, and I will call that point as point D. Right? So then what I will do, again, I will draw a straight line which will join sigma minus 1 divided by factor of safety and sigma y by factor of safety. So then thereby by doing so, I am obtaining the point, I am obtaining the straight line CD. Correct? Then what I will do, what does this Soderberg criterion state? The Soderberg criterion states that at any stress level which is below this triangle, any stress level below this triangle, it means that the design is safe, right? At any stress level which is above this triangle, any stress level above this triangle is not safe. This is what Soderberg criterion is stating. Now what I will do, I will consider a point on this line. So any point above this line, the design will not be safe. Any point below this line, the design is totally safe. So the limiting condition for this case is this line CD. So I will consider any point on CD, on the line CD, and I will call it as point P. You consider any point on this line, call that point as P, right? Then the stress amplitude when the component is subjected to this particular level is called this point as K, right? Then draw a straight line, from point P to x-axis, draw a straight line from point P to x-axis, call that point as E. Draw a straight line from point P to this point on y-axis and call that point as K. Call that point as K. So ಈ construction ಹೇಗೆ ಬಂತು ಅರ್ಥ ಆಗಿದೆಯಾ? Have you guys understood this construction? Any doubts so far, Mohak?
No, sir.
Okay. ಅರ್ಥ ಆಗಿದೆಯಾ ಇಲ್ಲಿ ತನಕ?
Yes, sir.
Okay, fine. So now what we will do, if you observe these two triangles, am I audible?
Yes, sir.
Okay. This is origin O. You observe triangle COD. You observe triangle COD and observe triangle PED. You observe triangle COD and PED. Are these two triangles similar? Are these two triangles similar? Triangle COD is similar to triangle PED. So since triangle COD is similar to triangle PED, so I can say that the ratio of their sides are constant. Howda? It means to say that CO by PE should be equal, CO by PE should be equal to say OE by OD. Howda? So what I will do from this property that is similarity of triangles, this length PE, the length of the line PE divided by the length of the line CO should be equal to the length of this line ED divided by OD. Howda? So it means to say that PE by CO should be equal to ED divided by OD. This should be equal to ED divided by OD. Now you consider this line ED. You consider this line ED. Now what is OD representing? What do you mean by the length OD? The length of the line OD, the length of the line OD is nothing but yield strength by factor of safety. Howda? The length of the line OD is nothing but yield strength by factor of safety. So this is sigma y by factor of safety. Now the line I am considering is ED. The line that I am considering is ED. Can I say that ED is equal to OD minus OE? Can I say that ED is equal to OD minus OE? Correct ಆಗಿದೆಯಾ ಇದು? I want someone to respond. ಅರ್ಥ ಆಗಿದೆಯಾ ಇದು? ಮೋಹಕ್?
sir.
ಅರ್ಥ ಆಗಿದೆಯಾ ಅರ್ಥ ಆಗಿಲ್ವಾ?
ಆಯ್ತು ಸರ್. ಆಯ್ತು ಸರ್.
Okay, fine. So ED is equal to OD minus OE. So I'll substitute it here. This is OD minus OE divided by OD. ಹೌದಾ? ಇದನ್ನ ಫರ್ದರ್ ಡಿವೈಡ್ ಮಾಡಿದ್ರೆ ಏನಾಗುತ್ತೆ? OD by OD, if I split it, OD by OD is 1 minus OE by OD ಬರುತ್ತೆ. ಹೌದಾ? So to say PE by CO is equal to 1 minus OE by OD is equal to 1 minus OE by OD. Now what is PE? Now what is PE? P anandreno, it is the stress level within this material. PE is nothing but okay. This is the distance PE. PE antandreno, I am considering stress amplitude along y axis. So this value PE is nothing but stress amplitude. Howda? So the value PE is nothing but stress amplitude. So substituting it here, this is sigma A. Now what is CO? What is CO? CO antandreno, CO is nothing but sigma minus 1 by factor of safety. Sigma minus 1 by factor of safety, that is endurance limit by factor of safety is CO. Now 1 minus, what is OE? What is OE? This is OE. Howda? OE ಅಂತಂದ್ರೇನು? What are we having along x-axis? We are having mean stress along x-axis. So OE is nothing but sigma m. So this is sigma m. Correct? What is OD? OD, as you can see, it is nothing but this length. OD is nothing but sigma y by factor of safety. OD is sigma y by factor of safety. Sigma y by factor of safety. Correct? Now, if I try to simplify this, factor of safety, which is at the bottom of the denominator, will go to the numerator. So factor of safety times sigma A by sigma minus 1 is equal to 1 minus factor of safety times sigma m by sigma y. ಹೌದಾ? ಸೊ ಇಲ್ಲಿ ಯು ಅಬ್ಸರ್ವ್ ಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಸೇಫ್ಟಿ ಎರಡು ಕಡೆ ಕಾಮನ್ ಇದೆ. ಸೊ ಈ ನೆಗೆಟಿವ್ ಸೈನ್ ನ ಇಫ್ ಐ ಶಿಫ್ಟ್ ಇಟ್ ಟುವರ್ಡ್ಸ್ ದಿ ಲೆಫ್ಟ್ ಹ್ಯಾಂಡ್ ಸೈಡ್ with factor of safety being the common factor, the expression will be of the form sigma A divided by sigma minus 1 plus sigma m divided by sigma y is equal to 1 by factor of safety. It is equal to 1 by factor of safety. Now this is the equation that represents Soderberg criterion. This is the equation that represents Soderberg criterion. What is it stating? Sigma A by sigma minus 1 plus sigma m by sigma y is 1 by factor of safety. ಈ derivation ಅರ್ಥ ಆಗಿದೆಯಾ? Have you understood this derivation?
Yes, sir.
Okay. ಏನಾದರೂ ಡೌಟ್ಸ್ ಇದೆಯಾ ಇಲ್ಲಿ ತನಕ?
ಫೈನಲ್ ಈಕ್ವೇಷನ್ ಕಾಣಿಸ್ತಿಲ್ಲ ಸರ್.
ಹಾ?
ಫೈನಲ್ ಈಕ್ವೇಷನ್ ಕಾಣಿಸ್ತಿಲ್ಲ ಸರ್.
Okay, I will rewrite it again. Just give me a minute. ಇವಾಗ ಕಾಣಿಸ್ತಾ ಇದೆಯಾ?
ಹಾ ಸರ್, ಈಗ ಕಾಣಿಸ್ತಿದೆ.
Okay, fine. So ಇದನ್ನ ಬರ್ಕೊಳ್ಳಿ. This is very important. You can I will share you guys the PPT. You can note it down later. This is very important derivation. Always try to remember it. ಇಲ್ಲಿ ತನಕ ಏನಾದ್ರು ಡೌಟ್ಸ್ ಇದೆಯಾ? Should I repeat it? Should I repeat it or shall we move ahead? ಅರ್ಥ ಆಗಿದೆಯಾ?
Yes, sir.
Okay, fine. Now, just give me a moment. There is some error. Okay, fine. Now, let us try to derive the expression for Goodman criterion. Okay. Now, let us try to derive an expression for Goodman criterion. So, here, what is that we have? Instead of yield strength, we are considering ultimate strength. Just give me a moment. Is my screen visible?
Yes, sir.
ಒಂದು ನಿಮಿಷ ಇಲ್ಲಿ ಏನೋ ಸ್ವಲ್ಪ ಹ್ಯಾಂಗ್ ಆಗಿದೆ ಸಿಸ್ಟಮ್. ಜಸ್ಟ್ ಗಿವ್ ಮಿ ಅ ಮಿನಿಟ್. Yes, just give me a moment. I'm unable to close this. Okay, can you guys see my screen now?
No, sir.
ಕಾಣಿಸ್ತಾ ಇಲ್ವಾ?
No.
Just 1 minute. Okay, can you see now?
Yes, sir. Can I see?
Okay, fine. So now let us try to derive the expression for Goodman criterion. As I was saying previously, the only difference between Soderbergh criterion and Goodman criterion is Soderbergh considered yield strength of the material along x-axis. He considered endurance limit of the material along y-axis. The difference with Goodman is, instead of considering sigma y along x-axis, he is considering the ultimate strength, that is sigma u along x-axis. That is the only difference. So what we will do, we will try to plot a graph where we have mean stress along x-axis and stress amplitude along y-axis. Note that mean stress is sigma m, stress amplitude is nothing but sigma a. So what he did, Goodman considered endurance limit along y-axis. You will call that point as a. Instead of considering sigma y, he is considering sigma u. You call that point as b. Right? This is the only difference. The rest of the thing is totally the same. Then what we will do, we will draw a straight line with joints a and b. Then in order for us to, the design to be safe, so we'll divide the sigma minus 1 by factor of safety, also sigma u by factor of safety. That is, we consider a point C which represents sigma minus 1 by factor of safety, and a point called D which represents ultimate strength by factor of safety, and then we will draw a straight line which will join these 2 points. Then what this Goodman condition states, at any stress level below this triangle or within this triangle, the design is safe, right? At any point or at any stress level above this triangle, the design is not safe, right? So blue color indicates that the design is safe, red color indicates that the design is not safe. Now what is that we need to do? We need to consider any point on this line CD. Let me consider a point called P. This can be any point on this line CD. Then I will drop a vertical line perpendicular to this x-axis, and I will call that point as E. Then I will drop a perpendicular from point P to y-axis, and I will call this point as, say, K. This point is not so relevant. You can call this anything. Now what we will do, if you can observe, so which 2 triangles are similar? Again, this is O, that is the origin. Triangle COD is similar to triangle PED. Triangle COD is similar to triangle PED. So their ratio of their lengths should be constant. Now PE by CO should be equal to, what is it? ED by OD, right? PE by CO should be equal to ED divided by OD. Now what is this line ED? This is ED, which is the difference between OD and OE. This line ED is the difference between ED and OE. So this is, sorry, OD and OE. This is OD minus OE divided by OD. So thereby, if I simplify it, PE by CO should be equal to 1 minus OE by OD, right? Now, if you observe, what is PE? PE, that is this line, is nothing but this stress amplitude. This is sigma A. So thereby, PE is nothing but sigma A divided by what is CO? This is CO. This straight line is CO. What is CO? CO is sigma minus 1 by factor of safety. Sigma minus 1, that is endurance limit by factor of safety. This should be equal to 1 minus, what is OE? This is OE. What is OE? OE is nothing but the mean stress induced in the material, right? So this is sigma M. What is OD? This is OD. OD is nothing but sigma U by factor of safety. Sigma U by factor of safety. Now what will happen? The factor of safety will go to the numerator. Factor of safety will go to the numerator. Then what will happen? I will shift this expression towards the right hand side of the equation. These 2 expressions are having factor of safety to be common on their numerators. So if I simplify, I will get an expression of the form sigma A by, sorry, yeah, sigma A by sigma minus 1, sigma A okay, yes, sigma A by sigma minus 1 plus sigma m by sigma u, which is equal to factor of safety, or I can take the reciprocal of this expression, which will give sigma minus 1 by sigma A plus guys, am I audible? ಕೇಳಿಸ್ತಾ ಇದೆಯಾ ನಾನು ಮಾತಾಡ್ತಾ ಇರೋದು?
ಯು ಆರ್ ಆಡಿಬಲ್ ಸರ್. ಇದು ಸರ್
Oh,
ಸ್ಕ್ರೀನ್
ನಾನು ಅಷ್ಟೊತ್ತಿಂದ ಹೇಳಿದ್ದು ಕೇಳಿಸ್ತಾ
ಕೇಳಿಸ್ತು ಸರ್. ಈಕ್ವೇಶನ್ ಎಲ್ಲ ಮಾಡ್ತಾ ಇದ್ರಲ್ಲ, ಕೇಳಿಸ್ತು.
ಫೈನ್ ಫೈನ್ ಫೈನ್. ಸೊ ಅಲ್ಲಿ ತನಕ ಲಾಸ್ಟ್ ಸ್ಟೆಪ್ ತನಕ ಗೊತ್ತಾಗಿದೆ ಅಲ್ವಾ?
ಅದು ಸ್ಕ್ರೀನ್ ಲಾಸ್ಟ್ ಅಲ್ಲಿ ಹೊಟ್ಟೋಯ್ತು.
ಇವಾಗ ಕಾಣಿಸ್ತಾ ಇದೆಯಾ?
ಇಲ್ಲ ಸರ್, ಕಾಣಿಸ್ತೀರಾ.
ನೆಕ್ಸ್ಟ್ ಕ್ಲಾಸ್ ಯಾರ್ದಿರೋದು?
ಪವಿತ್ರ ಮ್ಯಾಮ್.
ಪವಿತ್ರ.
Okay, just give me a moment. Okay, fine. ಇವಾಗ ಕಾಣಿಸ್ತಾ ಇದೆ ಅಲ್ವಾ?
ಹ್ಞೂ ಸರ್.
Fine. So now what will be the expression for Goodman criterion? Sigma A, that is stress amplitude by sigma minus 1 plus sigma m by sigma u is equal to 1 by factor of safety. This is the expression for Goodman criterion. This is the expression for Goodman criterion. Now you remember now what is Soderberg criterion? Soderberg criterion is sigma A by sigma minus 1 plus sigma m by sigma y is equal to 1 by factor of safety. What is Goodman criterion? Goodman criterion is sigma A by sigma minus 1 plus sigma m by sigma u, it is equal to 1 by factor of safety. Now you remember, whenever we make use of brittle materials, we will make use of Goodman equation. Whenever we encounter ductile materials, we will make use of Soderberg criterion. Note that the only difference between these two equations is we have sigma y in the denominator in case of Goodman Soderberg criterion. Here we have ultimate strength, that is sigma u. ಅರ್ಥ ಆಗಿದೆಯಾ ಇದು? Can you guys derive the equations stated here by yourself now? Am I audible?
Yes, sir.
Okay. So equations na ನೀವೇ derive ಮಾಡಬಹುದಾ? ಈ derivation ಅರ್ಥ ಆಗಿದೆಯಾ?
Then equals to f, ಇದು factor of safety ಅಲ್ವಾ? 1 by factor of safety ಅಲ್ಲ?
1 by factor of safety.
Goodman's criterion.
Denominator ಬರುತ್ತೆ, denominator of denominator ಬರುತ್ತೆ, ಸೊ ಅದು ನ್ಯೂಮರೇಟರ್ ಹೋಗುತ್ತೆ.
ಸರಿ, ಓಕೆ.
ಡಿನಾಮಿನೇಟರ್ ಆಫ್ ಡಿನಾಮಿನೇಟರ್ ಬರುತ್ತೆ, ನ್ಯೂಮರೇಟರ್ ಹೋಗುತ್ತೆ. ಸೊ ಲೆಫ್ಟ್ ಹ್ಯಾಂಡ್ ಸೈಡ್ ಅಲ್ಲಿ ಎರಡಕ್ಕೂ ಕಾಮನ್ ಇರುತ್ತೆ. ಇಲ್ಲಿರುತ್ತೆ ಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಸೇಫ್ಟಿ. ಈ ಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಸೇಫ್ಟಿ ರೈಟ್ ಹ್ಯಾಂಡ್ ಸೈಡ್ ಕಳಿಸಿದಾಗ 1 by ಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಸೇಫ್ಟಿ ಆಗುತ್ತೆ ಅಲ್ವಾ? ಓಕೆ ಫೈನ್. ಈ ಡೆರಿವೇಶನ್ ಅಲ್ಲಿ ಎರಡು ಡೆರಿವೇಶನ್ ಅಲ್ಲಿ ಏನಾದರೂ ಡೌಟ್ಸ್ ಇದೆಯಾ?
ನೋ ಸರ್.
Okay, fine. So next class ಅಲ್ಲಿ I will just there is one particular theory called as endurance limit modifying factors. Endurance limit modifying factors ಅಂತ ಇರುತ್ತೆ. So we'll make use of the same equation. We will make use of the same equation and we will modify this equation for a particular reason. We will do it and we will begin with problems from the next class. Nale probably, if possible, I will take 2 classes continuously. So be prepared. Nale in the problem shuru madana. So if you have got any doubts so far, we will discuss it in the next class, right? So you practice this derivation. If you have any doubts, we can discuss it later, right? So you can join DOM class now.
Sir, recorded class upload ಮಾಡಿ.